Assalamu alaikum dear students. I welcome you to 43rd lecture of probability and stochastic processes. We have been analyzing the behavior of finite state space Markov chains with possibilities of some states being transient and other states being recurrent. I hope you remember that it's not possible for a finite state space Markov chain to have all its states as transient states. So there will be some recurrent states, at least one. So we have been analyzing the transient or short-term behavior of such Markov chains using eigenvalues and eigenvectors. When I say transient behavior, I mean behavior before the evolution gets absorbed in the recurrent subclass of the Markov chain. Before that, the Markov chain, while going through its evolution, may be visiting transient states, and we want to know how many times on average these transient states are visited before the Markov chain gets absorbed in the recurrent subclass. We have been using eigenvalues and eigenvectors of submatrices of one-step transition probability matrix. One-step transition probability matrix or stochastic matrix of the whole Markov chain captures the transitory behavior or transitions and associated probabilities of all the states in the Markov chain. But if we group together transient states in one group and group together recurrent states in another group, then we can partition this stochastic matrix, and the submatrix associated with recurrent states is a fully stochastic matrix, and its higher and higher powers converge to a matrix which represents the stationary probability distributions of all the states in recurrent subclass, whereas the submatrix representing interstate transitions for the states which belong to the transient subclass is substochastic. Sum of its rows is not 1 for all rows, and higher powers of this submatrix gives us a matrix with all entries being 0. In other words, all eigenvalues of this submatrix have magnitude less than 1. And we found that if we want to find the average number of visits to a transient state before the Markov chain gets absorbed, then this number is represented by I, j entry of a matrix which is I minus q whole inverse. We applied this principle to a few simple Markov chains, and we are going to review the last case that we were discussing towards the end of the last lecture. And from there, we'll continue to expand our treatment of analysis of transient behavior of these finite state space Markov chains. We were discussing this small Markov chain with total states being 5. 2 of these states, 0 and 1, represent the recurrent class, and states 2, 3, and 4 represent the transient class. We had its stochastic matrix partitioned, and it looked like this, where the lower right submatrix is Q. This represents the interstate transitions for the group belonging to the transient class. And if we take higher and higher powers of this submatrix, it's going to give us all 0. But we were interested in the numbers which we obtained by taking the inverse of I minus q. This is q, so I minus q inverse is this. This is I minus q, and below that you can see is I minus q whole inverse. Then these numbers represent the average values of visits to different transient states before the Markov chain gets absorbed in the recurrent subclass. Let's put this matrix next to the graphical model of this Markov chain and try to see how these numbers can be interpreted in the transient behavior of this Markov chain. Let's look at this number. This is 1,1 entry of I minus q inverse. The first state in this group of transient states is this state labeled 2. So this 4 represents average number of visits to state 2 while starting from state 2 before this Markov chain gets absorbed in this recurrent subclass. Similarly, this number 5 represents average number of visits to state 3 when we start from state 2 before this Markov chain gets absorbed here. Similarly, this 2 represents average number of visits to this state with label 4. So if we start in state 2, on average, we visit it 3 more times. Remember, this 4 includes the starting visit. So if we start in state 2, we visit 3 more times this state again before we get absorbed, and we visit this state on average 5 more times before we get absorbed, and we visit this state for 2 more times. So how many jumps are required, or on average how many jumps does it take when we start from here and then get absorbed here? It is obviously sum of these 3 entries. So if we start from state 2, then including the first visit, we will take on average 11 steps. 4 plus 5, 9, 9 plus 2, 11. On average, we'll require 11 steps before we get absorbed in this recurrent subclass. Please remember, this number 11 is the average value of number of steps that you jump in the transient subclass before getting absorbed in the recurrent class. It's quite possible that actually when you are simulating this Markov chain, or if such a real life phenomena is happening, the number of steps that you observe in the transient class before you get absorbed could be more, could be less, but could be more, 20, 30, even more steps before you get absorbed. But on average, this is the average value, the expected value of total number of steps that you take inside this transient subclass before you get absorbed if you start from state 2. Let's look at other starting states. If we start in this middle state with label 3, the number of visits to this state before absorption, including the first visit, is 5. And number of visits to state 2 is 3, and number of visits to state 4 is 2. So total number of visits to all the transient states is 10 before you get absorbed if you start from state 3. And lastly, if you start from state 4, then total number of visits to this transient subclass before absorption will be on average equal to 6. 1 plus 1.5 plus 2.54, 4 plus 2, 6. So if you start from state 4, which is closer to the recurrent absorbing class, then on average you just take 6 steps and then get absorbed. But if you start from the faraway class with label 2, then you take on average 11 steps before getting absorbed in this recurrent class. The next case that we are going to consider is the example of a person trying to perform Hajj, where a person starts thinking about performing Hajj and starts gathering his financial resources. And at some point later on, he does apply for Hajj, and if his name gets selected in a random draw, he moves to the next state from where he is going to perform Hajj, or in the case of some unfortunate circumstances, he'll come back to the starting point. So all these states where he is trying to perform Hajj are transient states, and the state representing the event that he has performed Hajj is an absorbing state, because once he has performed Hajj, he stays there. Let's have a look at that class and analyze its transient subclass in terms of average number of visits to different states before getting absorbed in the last state, which represents that the person has performed. Let's have a look at the graphical model of this Markov chain. The graphical model of this random phenomena is shown on your screen, with state 0 being the recurrent state, the only state in the recurrent subclass, and these 5 states 1, 2, 3, 4, 5 are transient class states. So we are going to look at the submatrix representing all the transitions within this class and call it Q. Here is this submatrix Q, which is 5 by 5, and it represents all the transitions within this transient class. We are going to take the inverse of I minus Q. Let's take inverse of I minus Q, and it comes out to be this matrix with entries which are fraction of numbers. They have fractional elements as well as integer elements. So they are real valued numbers. We are going to interpret these numbers in terms of the average number of visits to different transient states before you get absorbed in the state labeled 0, which represents that the person has performed Hajj. So let's look at different numbers in this matrix I minus Q whole inverse. So if you start in this state 1, which is the logical state to start, then you will visit this state again 15.8 times before you get absorbed into this state. And when you start in state 1, you will visit state 2 1.7 times, and state 3 only once before you get absorbed. Similarly, state 4 will be visited 15.2 times, and state 5 will be visited 15.8 times before you get absorbed. All these numbers do make sense, because when you start here in state 1, 90% of the time you will move to state 4 and 5 and then come back, which represents that you have not collected enough financial resources to afford this privilege of having performed Hajj. So you will move from state 1 to 4 to 5 and back quite often before you get a chance to move to state 2. Once you move to state 2, that is, you do apply for Hajj, then you move to state 3 with more than half probability, and once you are in state 3, then there is a very high probability of 99% that you will actually perform Hajj. So the transient behavior of all these classes, all these states in transient subclass show that the average number of visits to state 1, 4 and 5 are quite large before you get absorbed, and the average number of visits to state 2 is just 1.7, and average number of visits to state 3 is just 1. Even though it's natural to start in state 1, but let's assume that you have started observing someone who is in state 2, who has moved to state 2. So if somebody starts in state 2 that he has applied for Hajj, then the number of times he visits this state again is 1.7. Number of times he visits this state before absorption, that is, he goes to this route or this route, is less, 6.8. So if you start observing somebody who starts here, then he visits this state only 6.8 times before absorption. Similarly, the number of visits to state 4 and 5 are 6.2 and 6.8. Let's assume you start observing somebody who is in state 3. So if he has already been selected to perform Hajj, then he is in state 3, you start observing him. Then number of steps he takes to different transient classes before he gets absorbed are shown here, which is 1 for this state, which is the original starting observing instance, and all other numbers are much smaller than 1. That is, if somebody has moved here, then the average number of steps he takes to visit these states are much less than 1, because most likely he will go here and get absorbed, and very less probability is there that he'll move back through this path of only 1% probability to transient states and visit them again. Let's have a look at one important aspect of this Markov chain, that is, if you start in state 1, what is the total number of steps on average that you take inside this transient class before you get absorbed here? That will be the sum of all these numbers. And if you sum all these numbers, it comes out to be 50.5. So if you start in state 1, then on average you take 50 steps in this transient subclass before getting absorbed. And remember, in 1 year there are 3 steps. So you start here, you either go here, here, or come back, or here, here, and come back. So in 1 year there are 3 steps. So if you take on average more than 50 steps in this transient class before absorption, then on average you have to wait for 17 years, because 17 times 3 is 51. So on average you have to wait for 17 years before you get a chance to perform Hajj. It does not mean that everybody who applies for Hajj will be waiting for 17 years before he gets a chance to perform Hajj. This is a probabilistic analysis. We are talking about average or expected number of years that a person has to wait. So on average, a person has to wait for 17 years before his chance comes up. But it's possible, if he's lucky, that he applies and he gets through. And it's quite possible, if he's very unlucky, that he continues to apply year after year and he does not get a chance for even 30 or 40 years. That is when he starts in state 1. If he starts in state 1, where he is still gathering his financial resources, still thinking about applying for Hajj, then it takes him to 17 years on average before he gets a chance to perform Hajj. This average waiting of 17 years is applicable if we start observing somebody who is in state 1 still thinking about performing Hajj. But let's start observing somebody who has already moved to state 2. That is, he has already applied for Hajj. In that case, total number of steps in this transient class before getting absorbed is sum of all these numbers. And if you sum all these numbers, it comes out to be around 22, slightly less than 22. So if the person has already moved to state 2, then total number of steps on average are 22. And if you divide that number, then it takes slightly more than 7 years before that person gets absorbed here. So if a person has applied for Hajj, has moved to state 2, then it takes on average 7 years before he gets absorbed in state 0. But our government has instituted a policy where if a person starts applying for Hajj year after year and his name is not selected in the random draw, then after 3 such unsuccessful attempts, his name is automatically selected, and if he applies 4th time, he is automatically selected and is taken for Hajj. That seems to be a nice policy, because if this is actually the model that this random population follows, then on average it takes more than 7 years. Hence, if you get a chance to perform Hajj for sure in 4th year, then it's a nice policy on the part of our government. So you can analyze a finite state space Markov chain in terms of its initial transient or turbulent behavior before its absorption into recurrent class by taking the inverse of I minus q and looking at its values. Different values represent average number of visits to different states when you start from a certain state. There is another way to look at these things, and this is called return times. So if a Markov chain, which is a sequence of random variables, is evolving, representing a time varying random phenomena, then different states are visited, and it's possible that this certain state is visited now, and after a few transitions it is visited again, and perhaps once more or few more times. But you know, if it's a transient state, it's going to be visited only finite number of times. If you start observing it when it has visited a state and see how many jumps does it take before the next visit, that we can call the return time. So if you start your observations at sampling instance 0 and assume that the random variable is in a certain state j, then the minimum value of sampling instance greater than 0, 1, 2, 3, 4, 5, whatever, when the state comes back to state j, when this Markov chain again visits this state j, is the return time. And of course, if that state is a recurrent state, then there will be a second return time, a third return time, and so on and so forth, because a recurrent state is going to be visited infinitely often, whereas a transient state is only visited finite number of times. So it's obvious that this concept of return times is more applicable to recurrent states because they are visited again and again and again. So average number of visits before absorption is applicable to transient states, and the average amount of wait before that state is revisited is more applicable to the recurrent states. So we are going to analyze this concept of return time in terms of the stationary probability distribution of recurrent states. Once again, this idea of average return time is more applicable to recurrent states. So let's do this analysis. So if we know that we are in state j at sampling instance 0, then the first return time is the next time that this state is going to be visited. If it's a recurrent state, it's going to be visited again and again, but will take minimum of such sampling instances, minimum of these indices, minimum over n, such that xn is again j, but n is greater than 0. For sampling instance 0, we are in j, and then for all other sampling instances, all the other indices, when we are again in j, we are going to take the minimum of all these numbers. So that will give us the first return time. Of course, there will be a second return time, and that will be when we are again in state j. We'll take minimum of all the indices, but now we are going to restrict our n to be larger than t1. So if we take larger than t1, the index where we are again in state j, and subtract the index for the first visit, then this is the second return time. So first return time is that after you start from a certain state, what is the sampling instance that you come back to that state for the next time. And the second return time is that you start counting from that second visit and see how many steps it takes for the next return. Of course, these are going to be random numbers, these return times. It's quite possible that if you start from state j at sampling instance 0, then come back to that state in 5 steps, and next time you come back in 7 steps, and next time again 5 or 6, any number of steps. Because this is a random variable, it can take any value. But if you take a large collection of these return times and take their average, they are going to converge to the actual expected value of this collection of random variables. Why? Because of law of large numbers. So from law of large numbers, if you have first return time plus second return time plus third return time all the way to k return times, and you take the sum of all these return times, which can be different, but you average them out by dividing this sum with k, you are going to converge to the expected value of return time for that particular state. And this is the actual expected value of the probabilistic model which these return times are going to follow. So if you take this k to the right side, then k times the expected value of return times is the total sum of all these return times. So that's the total number of steps that the Markov chain is observed for, and in these total number of steps, the visits to a certain state is only k times. So k divided by this whole sum of all the observed instances is the fraction of time that the state is visited, and that is nothing but the stationary probability associated with that state j. So if we are working with state j, then stationary probability distribution associated with that state j is number of times that state is visited divided by, on average, total number of observations that lead to the k visits. Since k gets cancelled out, it's easy to see that expected number of this return time value is 1 over pi j. So for a recurrent state j, the expected value of return time to that state j is 1 over the stationary probability value for that state. So this expression of expected value of return times associated with a certain recurrent state is the reciprocal of the probability, the stationary probability value associated with that state. This makes sense because the stationary probability associated with a certain state represents the fraction of times that state is visited for a large observation window. So if the Markov chain has moved into this recurrent class and a certain state is only visited 1% of the time, then 99% of the time the Markov chain stays in other states. So the return value is, on average, after every 99 steps on the other states, and then the 100th step is for the same state. But if the probability value associated with a recurrent state is a large number, say 0.2, then fraction of times that state is visited is 20%. So out of every 5 steps in that recurrent class, there is 1 step for that state and 4 steps away from that state. Hence, the expected value of return time will be 5, or 1 over the stationary probability value associated with that state. Let's apply this principle of average return times as reciprocals of stationary probability distribution to a few cases of Markov chains which have recurrent classes. The first example is a simple two-state recurrent Markov chain where the probability of moving to state 0 from state 1 is p, and probability of moving from state 0 to state 1 is q. The remaining probability is associated with remaining with particular state again and again. We have analyzed this problem previously, and we know that stationary probability distribution for these two states 0 and 1 is equal to p over p plus q and q over p plus q. If we want to find the expected value of return times associated with state 0, then all you have to do is take reciprocal of this figure and you get p plus q divided by p. Similarly, the average value of return times associated with this state is p plus q divided by this q. Let's take a few numerical values for this p and for this q to see what these return values are. Let's suppose our Q is 0.9 and our P is 0.8. So there is 80% probability that on next step we'll move here. If you just fit in these values, you get your stationary probability distribution value of 0.47 and 0.53. Then expected value of return time associated with state 0 is 2.1 and expected value of return time associated with state 1 is 1.9. So it appears that after every 2 steps, on average, not every time, on average, after slightly more than 2 steps, you come back to state 0, and slightly less than 2 steps, you come back to state 1. So this is probably what is going to happen. You start from state 0 with 90% probability you go here, and with 80% probability you come back. But sometimes you go here and stay here for some time before coming back. And it's also possible that you stay here with probability of 0.1. So average value of all these return times, which could be 1 in this case, or it could be 2 if you just go there and come back, or it could be 3 if you go there, spend one more sampling instance there and then come back. So all these return times of 1, 2, 3, they will give you an average value of 2.1. Let's change these numbers. Let's make these Q and P much smaller by a factor of 10. So if Q is now 0.09 and P is 0.08, then there is a high probability that you will stay here. With 92% probability, you will stay in state 1 sample after sample. Similarly, there is 91% probability that you will stay here in the state 0. But the ratio of P plus Q over P, or other way around, is going to be same, and your stationary probability distribution is going to be the same. Hence, your expected values of return times is going to be the same as before. So what's the difference? We have changed P and Q by a factor of 10. Now probability of jumping from state 0 to 1 and 1 to 0 is much less, and probability of staying in the same state where you were in the previous sampling instance is quite large. But average value of return times associated with two states are same. Something must have changed, but the average value is same. So what is it that have changed? Let's have a look. In previous case, when Q was 0.9 and P was 0.8, the more likely path was that you jump here and then you jump back. With 90% probability you jump here and then come back with 80% probability. So more of the jumps were of value 2, and the probability associated with this jump of 2 was quite large, and probability associated with jumps of say 1, 2, 3, 4 and then 5 were quite small. But if you look at this new scenario where probability Q and P are very small, then more of the jumps are like this. Let's look at state 0. It's quite often this is the case that you will stay in state 0, and again stay in state 0. But if by chance you move to state 1, then you are going to stay in state 1 for quite large number of jumps before you come back. So in this case, the probability associated with return time of 1 will be quite large, but probability associated with 2 and 3 and 4 will be small. The probability associated with very large return times will be appreciably larger, that it is quite possible to spend 10 transitions here before you come back. So in this case, the probabilities associated with large return times is large, hence the variance or spread in this case is quite large. Previously, more probable event was that you come back in 2 steps. Now, more probable event is that either you come back in 1 step or come back in much large number of steps. But in both cases, the average value of return times is same 2.1 for state 0 and 1.9 for state 1. So average return times associated with different states in a recurrent class tell us just this information, that is the average value. It does not tell us anything about the spread or actual probabilities associated with different return times. So this information of average return time should be used carefully, and other pieces of information should also be used, which are variations, variance, and other higher moments of this random variable, which is the return time associated with different recurrent states in a recurrent subclass. Let's apply this principle of finding average values of return times as reciprocals of stationary probability distribution to another case. That case is that electronic device which breaks down and is either repaired locally or in a specialized repair facility. That Markov chain was also a recurrent Markov chain. So let's apply this principle to that problem. So the graphical model for this 3-state recurrent Markov chain is shown here with associated probabilities. And we have analyzed this problem previously, and we have found that under these values of transition probabilities, the stationary probability distribution associated with these states are 0.04 for state 0, 0.09 for state 1, and 0.87 for state 2. These numbers also make sense because once you are in state 2, you stay in state 2 with 90% probability. So stationary probability associated with state 2 is large because you stay here with 90% probability, and with 10% probability you move here and then come back quickly or spend some time in state 0 before you come back. Let's find the average return times associated with these 3 states. So average value of return time associated with state 0, which is reciprocal of 0.04, is 23. It should be 25, but due to the shortage of space, I have just written these numbers with an accuracy of 2 digits. Actually, this is 0.04 something 3535. So this number is actually larger than 0.04, hence the expected value of return times associated with state 0 are 23. Which means that if this Markov chain represents a random phenomena, which is the observation of state of a machine every morning, then the machine returns to this state 0 every 23 days. So it goes back in the working condition, serves its purpose, then breaks down, does not get repaired here, and comes back. And this happens on average every 23 days. Let's have a look at the return time associated with state 1. It is 11.5. So on average, every 11.5 days, the machine reaches here, and it either goes back or is sent to the specialized facility the next day. And the return time associated with state 2 is 1.15, which means that once it goes out of this state, it comes back after slightly more than 1 day. It either comes back immediately next day when it is repaired in the local facility, or it spends some more time and stays in this state 0 and then comes back here. But on average, the machine is repaired in 1.15 days. With this, we conclude our discussion of Markov chains with finite state space. we learned that if a Markov chain has a finite set of states that it visits, then some of the states could be transient, but there must be some states which are recurrent, which are visited infinitely often, because Markov chain is observed for uncountably infinitely many sampling instances. But in real life, not all Markov chains can have finite space. There are Markov chains which have countably infinite states in the state space. There are many examples, and one example that we talked about a few lectures ago when we started the discussion of Markov chain is the number of descendants of some famous person. Here we are talking about a subsection of human population, and we simply cannot put an upper limit on the size of this subgroup. If this world does not run out of its resources, this population can grow and grow, and it will continue to grow as we continue to observe its size as the Markov chain evolves. So if Markov chain has countably infinite state space, then the transition probability matrix will be of infinite size. So we have to be careful while trying to deal with these matrices. Actually, we do not try to deal with these matrices, we just look at individual values. So in this supposedly infinite size matrix, the values will be the values of transition probabilities. So transition probability from I to j is once again using the old definition that we move from state I to state j at sampling instance n to n plus 1, where I and j are two states and their labels I and j can be in set of natural numbers or any other set of countably infinite elements like set of integers or set of all lattice points on two-dimensional discretized plane. So this set of states is countably infinite, and you move from state I to state j in one sampling instance, and you call this transition probability. Since we are dealing with infinite size matrices, we have to be careful when we say that the sum of these transition probabilities over a row should give 1. There is no such row because we are dealing with infinite size matrices. But in general, if we sum these transition probability values over the second index k, then you are summing over all possible jumps starting from state I. And the transition probabilities of all possible jumps from state I to all other possible states in the whole state space should sum up and should give you 1, because this collection of all possible jumps represents the whole sample space of the underlying probability model. So these are the transition probabilities, and they fulfill this summation criteria that they should sum up to give us a value of 1. Now let's have a look at a few simple cases of Markov chains with countably infinite state space. The first example is of a random walk. This random walk is on states labeled with positive integers or natural numbers. So states are 1, 2, 3, 4 all the way towards going infinity. And the transition probabilities associated with this countably infinite Markov chain are shown here. In general, if you are in a state, then you move towards the state on right side with probability p, and you move towards left with probability 1 minus p. This applies to all states but state 1, which is the end state, and it has a perfect deflection. So once you reach state 1, you always move to state 2, and for all other states, when you are in a certain state, you move towards right with probability p, and you move towards left with probability 1 minus p. So you can write these transition probabilities here with the exception of this transition probabilities from 1, which is always 1 with transition going towards state 2. The next example is an extension of this random walk, where we walk on a two-dimensional grid. I have not labeled the states here, they have been left empty, but this collection of states is located on sampled grid of two-dimensional plane. So there are infinitely many states, and from any given state you move to its neighboring states with some probability, and similarly you can move back. I have not even labeled the arrows. It's quite well understood that one of the arrow points to the right, then the other arrow points to the left. So this is a huge complicated Markov chain located on two-dimensional grid with countably infinite states with transition probabilities associated with neighboring states shown here without actual numbers. You can put on any numbers, reasonable numbers that you want, but the model of this huge Markov chain is shown to you. When we have Markov chains with countably infinite sized state space, then their analysis using eigenvalues and eigenvectors is not possible because the stochastic matrix is of infinite size. Similarly, the analysis of such Markov chains in terms of their transient or recurrent behavior is not so easy. It's quite possible for a Markov chain to have all its states as transient states, whereas in case of finite sized state space, it was necessary for the Markov chain to have some states as recurrent states. This restriction could be removed for the case of countably infinite state space Markov chains. But we can still talk about these countably infinite state space sized Markov chains to be transient or recurrent. So if a Markov chain has infinite state space and all the states are recurrent, then this Markov chain is called a recurrent Markov chain. And in that case, if we define R to be number of visits to a certain state J, then this state is going to be visited infinitely often, and this number is going to be infinity. But if the Markov chain is not recurrent, its states are transient, then this number is going to be less than infinity, a finite number. In any case, if you want to find the expected value of R, the number of visits associated with a state, then based on the analysis we performed a couple of lectures ago, this is nothing but summation of n-step transition probabilities from state J to J. So if you move from state J again to state J in n steps, you are revisiting that state, and you count all these probabilities of moving from state J to J in n steps, where n can vary from 0 to infinity. So that is going to give you expected value of number of visits to a certain state. And if that number, this expected value, comes out to be a finite number, then this Markov chain is a transient Markov chain. And if that number comes out to be infinity, then this Markov chain is a recurrent Markov chain. As I said earlier, analysis of Markov chains with infinite state space is not very easy, and it's quite possible for a Markov chain to have all states as transient states. The analysis is based on simple mathematical tools that you can look up in any good book on Markov chains. I leave that investigation to you as a do-it-yourself assignment. With this, we conclude our analysis of Markov chains, and from next lecture, we're going to look at other types of stochastic processes. Till then, I wish you the best. Thank you. Khuda Hafiz.